Now, Komal Didi with us from MS-18. She's doing her master's thesis in detection of exoplanets. So I'll hand it over to her.
Yeah, thank you. And hi everyone, I'm Komal, as you introduced me. I'm from MS-18 batch. And today I'm going to talk about my research work. And also give some introduction to the world of exoplanets. And first of all, I thank you all for coming here. This is so cold outside. And I'm hoping you all are from mixed batches, first year, 4 years. 4 years. So, if it gets older, I try not to keep the level very high because even I find some topics very hard to learn. So you can ask me questions later. Okay. So I'll start now. So exploring the exoplanets. I like to use the word exploring because it's like you can do. It's a very new topic. So there are a lot of areas which you can explore. So it's not like already a lot of work has been done. So you can even you can think of something to do and you can try that in it if you study about it. So yeah, so there is a short history. My first project was in evolution. So when I came here, as many of you are also confused between majors, so I was confused between bio and physics. I was told that gradient in physics is very hard, but do you want to choose that? And then bio department seemed very nice, diverse. So I thought why not try start with bio. But then it went nice, but I thought why am I not like hesitating to try physics? Then I also liked that. And then I tried working on taking some reading projects in winter, like from Abhishek sir. And then I was supposed to do my second year summer in experimental condensed matter out of ISL, but COVID happened. So that was my way to explore that if I can do experimental physics and I can enjoy it, means that is like a big step that I can also move ahead. Because when you do experimental work, then not only do you work with the instruments, you also analyze the data and you study the science behind it. So it's a combination. So once, if you get the chance, you should always try that also. Like the labs, I think you may be learning a lot in the lab. Like, I mean, if you're given time to like complete one project in 2 or 3 sessions or in 2 or 3 weeks, you study a lot about it before the Viva especially. Then you understand, okay, I actually don't know a lot of things. So yeah. And then during COVID, so there was this course, it happened in this classroom, right? MSA people must know it, by Kulendra Pal Singh. Sir was teaching us Introduction to Astronomy and Astrophysics, and that is when our semester stopped. And I was not studying much during the classes, but it was just the first mix-in, so we all were just, getting introduction to it. But when COVID happened, I used to study it a lot. Like I don't know why, there was nothing to like motivate me, so I just chose this and started studying it. The book by Raj Chaudhary, and I enjoyed it. And then I did some online courses. We had EDX and Coursera, Open Select, and all. I used to explore them very nicely, and I was like, oh, there is so much happening. Why are we not trying? I mean, it's also like so many topics are not like in India. So there is very less people working on those topics in India, maybe a handful, 2 or 3. So we don't know. We just think at our own institute, if there are 2 or 3 fields, we should not think that that is the end. There are so many topics, so you should never hesitate. You should keep trying. So that was when I sent so many emails. I was away from everything, as you know. I was thinking I'm lagging behind. I sent so many emails, approached people. Even if you get rejections, that should not make you lose hope. So that's when I got a project in exoplanetary transit flight curves, and our summer was extended. So I also got another project. So sometime like throughout the semester and all, I somehow managed, and I worked on like title like exoplanetary atmospheres and also on exoplanetary transit flight curves, and then. For my thesis, I'm working on radial velocity precision. And there's also a side project which I've been working on for a few months, which is on planetary atmospheres. So this has, and I've been liking it. So when I like one project, it led me to email something that unrelated. And this is how I've grown in this field. So just one thing, just never think that you cannot do something or you're lagging behind. You can do a lot of things. And so this is an image of cotton candy planets. The density is almost like that of a cotton candy. I just found it interesting, so I included it here. And what are exoplanets? I think most of you must have heard by now, but it's like they're like extrasolar, the planets which are not in our solar system. So now when we can send telescopes far behind and all, and we found out the existence of so many other planets which are rotating around different stars. So this has they were first discovered in around 1992, taking around some pulsar thing involving, and the closest exoplanet is Proxima Centauri B, I think around 4 light years away from Earth, and they're mostly found in a very small region of the Milky Way galaxy. So here is an artist's depiction of a six-planet system orbiting a distant star. So the range of the exoplanets is very diverse. They can be as large as gas giants like Jupiter or Saturn, and they can be small like Earth or Mars. And they are very also like okay. There is also a range like terrestrial planets which are also called as rocky exoplanets. They are around the range of size of Earth, as I told. And there are super Earths, which are more massive than Earth, but they're lighter than Neptune and Saturn. So this is Neptune-like planets, and then they're like gas giants, similar to size of Jupiter or Saturn. And some exoplanets are like covered in deep freeze. Like you keep anything there, it will freeze by the moment you keep it there. Whereas some are very like they have metals boiling inside them. So there is a very long range of the temperature. While some exoplanets have tight orbits, like they do revolve, and it can also be very short, like 2 days. And whereas some exoplanets are rogue, like they are orbitless, they do not have a revolve around the star, so they are just wandering on their way in the galaxy. And the detection methods mostly are like radial velocity transit, photometry, direct imaging, gravitational microlensing, and astrometry. There are more methods, but the percentage of detection of exoplanets by them is very less. Mostly it is done by transit photometry and radial velocity. And so, yeah, so in radial velocity, like the Doppler effect, like stars hover in space, that is how you detect them. And in transit, there is dimming of the star's light. I'll explain it in more detail. So the first detection technique is transit method. So it measures the minute dimming of the star as the planet passes between the star and Earth. So this passage is called a transit. I'll play this video. So if there is a star and a planet is passing, and you are observing the light of the star, when it will pass, it will be like kind of like an eclipse, like situation that you won't. There will be dimming in the intensity of the light you observe, and when you see that over a constant period of time, like regularly happening, there is a planet orbiting that star. So that is how you detect it, and also you can see this curve. So this is the changing. There is this dip coming in its intensity when it is coming in front of the star, the planet is, and it's going out. So this is the basis of it, that you observe the light and you observe the dip in the intensity, and then and when you observe it constantly, it means there is a planet. So yeah, this is called the light curve. When you compare the brightness of the star over time, so this is how you observe it. And this is also called a transit. When it completes one cycle, it means one transit. And the transit depth is very important because it is, as you can see in this equation, it somehow depends. I've not included all the factors, but it will come down to, I should have put the approximate sign, but it is also fine because sometimes you simplify and use this. So radius of the planet. So radius of the planet and radius of the star, the square of this ratio is proportional directly to the transit depth. So the more depth you see, the more you know there is dimming in the light, and maybe the planet is larger in size because it's blocking the light more. So this is how you can determine the size or radius of the planet. And because when you know the radius of the star, you can put in the values and find this out. Also, not only the size, transit data are also rich with other information like about the atmosphere. So because many there will be absorption, transmission, and all. So when you work this out, you will get to know a lot of things. So this is like very much richer information. So you know the tests and all, everything. So yeah. So now with that topic, I'll be telling about some of my work. So I did one summer last in 2021, and this was done at Tartu Observatory online. And yeah, so there is this ARIEL space mission, like the atmospheric remote sensing infrared exoplanet large survey by the European Space Agency, and some countries, and then I think US is also included in that. So it aims to study like what are exoplanets made of. Okay, now enough of detection of exoplanets, but what are they made of? And how do planets and planetary systems form and evolve? And what are the physical processes shaping the planetary atmospheres? So why this is special is because this is survey of a diverse sample of about 1,000 exoplanets, and it is the first mission which wants to measure the chemical composition and thermal structures of transiting exoplanets. So it's like you know exoplanets are there are so many exoplanets, but you don't know whether how is the chemistry of the exoplanet related to its host star, and how is that similar? Okay, you know there is a population of gas giants, but how is it related? How are many other things related? Can we club them into some more things? So that is why you want to bridge this gap in the knowledge of how plant chemistry is linked to the environment where it is formed, and or whether the type of host star drives the physics and chemistry of the planet's evolution, because it is going to evolve. So how is the host star going to affect it? So my role as an intern was that because the mission is going to be launched in 2029 and it's going to be a 4-year mission. So when you are operating on a mission, you get limited time to have the data and put it on use the for the target and all. So you want the mechanism to be very precise. That if you get the limited time, it has to be perfect. Like you know when to measure it, when not to measure it, which target to use, which one is going to give better results, which one focus on first. So my role was to develop. So it's not like I worked like entirely. It was a very small role because I didn't got accepted some years ago. It will be commissioned in 2029. So everyone around the world is working like to devise a mechanism, a perfect mechanism, a perfect pipeline for the mission. So I developed a compact mechanism. I don't know if it will be surely used or not, but I hope so. So to obtain the transit light curves. So in the observatory, they were taking the data of some targets and had to fit those define like they kind of refined it. Then little bit normalization I did with the data, and it was mostly observational only. So I fit those light curves. So very compact mechanism like You do not want to make, there are many ways to fit light bulbs, but you want it to be so compact that anyone can look at it and you can use it as it is. And then there are some air mass corrections or other things, and different kind of populations of exoplanets have different parameters to be employed. So you want to make that pipeline very compact and easier to be used by anyone. Because if it is going to be used by people in the mission, so it should be very nicely implemented. So this was my work, and we stretched it a bit after because a project cannot be completed in just 2-3 months. If you want that experience, you can learn the techniques. But if you are working on something, it will take some time. So yeah, and so this is just a very basic example of light curves. I just chose these two targets because the shape is very different. So as you saw in that video, there is a dip. So this dip. This is the transit depth, and which we obtain. So we calculate it, and we vary some parameters like the radius of the whole star or of the planet, and 0 point parameters or something, and metallicity. So there are n number of things which you can vary as you keep them as freely varying parameters or fixed parameters, and then you fit them and you see the changes, what model works best. So this is how I work upon this. This is the first thing I obtained slightly, but I like it because there are so many planets which they had at that time, and every exoplanet had a different depth shape. So as you can see, it will be very weirdly going up somewhere. Some have triangle shape, and it was just nice to see. So this is also to observe that the period it is like covering the star, like the more the depth, the more will be its size. And now I'm moving on to the second detection technique, that is the radial velocity method. So a star does not remain completely stationary when it is orbited by a planet. So it will always wobble. So it is based on that. So you can see this wobbling happen. The planet is revolving around it, but the star is also wobbling. And you can see this shift in the wavelength. Okay. So yeah, the star wobbles, changing the color of the light astronomers observe. So the Doppler effect causes the shift in the wavelength of the star's light. So when you are observing the star and you see the shift in the wavelength, you know a planet is passing by, which is causing it to wobble. So this is again a method of detection of the exoplanet. So you can see here, the star and planet orbit the common center of Mars. And the spectral lines move towards the red as the star travels away from it, and they move towards the blue as the star travels towards it. And this is different scenarios. Yeah, so using highly sensitive spectrographs to track a star's spectrum and searching for the periodic shift in its spectral wobbles is what is aimed by the radial velocity method. So that is why you see a lot of spectrographs being employed these days. And 51 Cassini was the first exoplanet detected by the radial velocity method. And this is an instrument called a spectrograph called NEID, on which I'm working for my master's thesis. This is a solar spectrum, just like seems very nice, so just I put it for reference. And this is PEG-CD. So the main aim of my master's thesis project is like to mitigate the effect of solar contamination, like in spectroscopic searches for extrasolar planets. So that is because when you observe, there will always be contamination, there will always be noise. So they commissioned this instrument in 2020. So before commissioning, they did a lot of work on how to reduce the contamination. But now that the data is actually coming out, they need someone to actually check it, to use all the techniques to verify whether it's actually getting removed or not, like whether the data I'm getting is correct data or not, like, and how to remove it, whether what we assumed before, can we actually make it happen? And if there are some factors they missed, if you're not getting correct results, there is something more. So also like when they were working on it, they wrote some papers. So they assumed some factors, but then they also mentioned it may also happen. So there are n number of factors which still can contaminate the data. So I have to work to correct the data. And this is kill peak. This is where the spectrograph is placed. So my supervisors are Dr. Joe Nyman, and my local supervisor is Professor Jasdeep Singh Bagla. And these are so this is an instrument funded by NASA and JWST, and it was made at Penn State. And my guide is currently at TFR, and I'm at ISIL. So yeah, so this topic is something I do not want you to go into detail or worry if you don't understand it, because I have time to understand it too. So I just have kept it because I want to use some terms. So this is like the cross correlation function, you may know, is like it is between two different signals, and it is defined as the way of similarity or coherence between one signal and the time delayed version of the other signal. So CCS will help us read the measurements of radial velocity. So you just want to see how, so in the data reduction pipeline, they have the data, they want to process it first, right? So they use this CCF technique, and radial velocities are derived by close correlating target spectra with a weighted numerical stellar mass based on spectral type. So there is some technique called masking that will mask some value, and that is like classical masking, classical mask-based technique or template mask-based technique. So you need not worry about it. I took time to even like I've discussed. It took, so that is like you put a mask and you vary, you see the cross correlation between them, and then that is how you process the data. So that gives you the cross correlation function, and on one axis you have the velocity. So that will help us get the radial velocity in the output. So that will give you the radial velocity. So what is the effect of solar contamination? Like why do we want to correct it, and why is it so important? So terrestrial mass-like planets, that is planets with the mass of Earth, who are orbiting sun-like stars, they use Doppler effect signals of 10 centimeter per second. So they have done studies and they have found out these values of precision for so many planets orbiting different kinds of stars. And when you see the value for the sun-like stars and which are orbited by Earth-like planets, the value comes out to be 10 centimeter per second, and which normally defines the radial velocity precision you want in your spectrographs. Like, you want that precision which will help you correct the data and get good values. So solar contamination due to moonlight and atmospheric scattering of sunlight can cause systematic errors in the stellar radial velocity measurements that significantly detract from the 10 centimeter per second sensitivity. So when there is noise, you cannot get the right precision. So addition of low level spectral contamination at variable effective velocity offsets introduces systematic noise when measuring velocity using classical mass-based correlation techniques. It is also true for template-based, but as of now, what I saw in the pipeline, they had used classical mass-based techniques. If you want to read anything in more depth, I can send you the links later. You can DM me or ask me. So, like, we want the precision, but we are not getting the precision, the main idea is because of the solar contamination. So that is why even if you have been to some observing session or something, or you have read about it, there is a fixed time you have to observe. But you have to start observing before that, and also observe after that, and you have to correct for the data. You have to see the twilight time and all. So that is because you do not want any contamination, and you also take background data for control. So here comes NEID. It is an astronomical spectrograph which is deployed with a 3.5-meter Band telescope at Cape Peak National Observatory in Arizona. It uses simultaneous spectrometer sky fibers that could reliably reduce the source of error to below the photon noise limit of typical stellar wavelengths. It uses a dedicated sky fiber. So what is special about it? It has a different fiber called a sky fiber, which is employed directly to sample a solar contamination spectrum at a resolution identical to the target spectrum. So, which is not what you will see in common spectrographs like the halves. So this is special that this has a different sky fiber, and its full form you can see and then explore exoplanet investigations with Dr. Spectroscopy. NEID. So this is a NEID fiber head. As you can see, I was talking about sky fibers. Is it clear here? Yeah, so they have one science fiber which will get the spectrum for a target and the sky. And they have one sky fiber which will get it for the sky. And then you will want to subtract the spectrum of the sky from the science to get your target. And there is some information about it, but I think they are fine. And they have some more better fibers that we can even use in our readings, CF in general. And this is something which even we want to explore more. Yeah, so as I was talking about, yeah. So this is like the weighted mask technique. So you mask some readings and you do like just mask it at a fixed value. And it was all done before I started the work, so it's not something I had to do, but I just included it. So you have the sky fiber spectrum and you have the science fiber spectrum. As you can see, the science fiber has target plus the sky, but you want only the target spectrum for your readings. So you have to correct that and subtract that. So that's not as easy as that. You have the data, you have to process it, obtain the CCF, and you have to be sure whatever you are obtaining is actually right. You have to verify it. And so yeah, and then you will finally get the target RE, radial velocity, from the resultant corrected CCF. Also, these are just like depiction. The actual values are not like comparable like this. This is just for like example description. So this is something I've included, like in the process, like how the things were crazy like this, and we had to get some nice values. So this is for Bernard star. So I got some targets and like some data, like which were extensively observed because we wanted to test something which has been observed a lot. So we can have more data and verify results. And this is how I obtained the CCF. It was very like hectic, but then finally we got it. And because the files and all, and when you're working in a team, you also have to understand things done by others first, and then how you have to implement that and start your own. And yeah, and also one thing I like about them, they have the team has already made so many better things. Like they have also made one exposure time calculator for the instrument. So if I want to calculate the exposure time or signal to noise ratio, I can put in the values and I can get that. And I obtained the signal to noise ratio because I wanted to scale down one spectrum. So that was something interesting I learned in this project, how to scale down a spectrum using the signal to noise ratio. And I've just included it just to show. But as I said before, the main goal, I did not you need not worry about the process. So is that I want to correct it and apply the technique to all other targets as well. Because in the end, it will be used for every target. So it doesn't have to be one target based. So what I'm working on has to be such that it can be used on all different stars as well. So I have to subtract the scattered solar spectrum observed from the sky fiber from the science fiber's CCA, and then I have to correct for it. Thus, what we want to do is mitigate the deleterious effects of solar contamination on our radial velocity precision and create realistic spectra that can accurately model the absolute flux and noise inherent to different levels of sky brightness. Hence, it can help us in identifying the different habitable zones around terrestrial planets. So, next I'll be moving on to my work on planetary atmospheric growth. So, in one of my summers, I worked with Dr. Vincent Chevrier and Dr. Cassini, and the project was based on Titan-like exoplanetary atmospheres. Now, why Titan-like exoplanetary atmospheres? So, Titan is Saturn's largest moon. It has thick nitrogen-dominated atmosphere, which is thought to be a potential harbor of life. There are assumptions that maybe in deep rock, seas or below the surface, there is some possibility that life could have existed over there. So, because also it boasts the hydrocarbon rivers, and which could potentially harbor strange life. And also the smoky haze of Titan-like exoplanets can be visible in the near future. So they want to work more on this aspect because with the coming telescopes, they expect to get better data. So they want to be ready with the tools. And yeah, so my goal was to record data using Planetary Spectrum Generator. So this is a calculator built by the NASA GSFC, and it's a very nice calculator. If you go and check it out, it has simulations from different telescopes for different planets, and you can put in values of different atmospheric compounds. You can change their abundance. You can change the pressure, temperature. Even you can add more particles in the atmosphere. Like you can add haze particles. You can change their radius, and you can explore and you can get some spectrum. You can record the values, and you can use that to see patterns happening. Like even for just exploring, it's also nice. So I wanted to use it to see if we see any patterns which can be explored later. So my work was to check for the collision-induced absorption patterns or like spectral irradiance patterns based on phase abundance, percentage, or the grain size. And I think I already told about planetary spectrum generator. So this is one vertical profile of the spectrum. So this is just one part of it. So as you can see, it is very interesting. You can change so many values. It's just vertical profile. There are more parameters which you can change. So I could just include this in one screenshot. So using this, you can change so many things, and it is very interdisciplinary. Like you need not have a proper knowledge of just physics. Sometimes having multiple courses in the 4 years actually helps, because nowadays no work is just one thing. It will involve different things. And some of the data details are like we chose some gases for the start, which we thought were more abundant in Titan. So should be more abundant in Titan, like exoplanetary atmospheres. So we kept smaller temperature range, higher temperature range, like the grain size of the haze particles. We changed that, and haze abundance also. And like plots were obtained by changing various things. This is one basic plot. And just to show that we took the ratio of the size. So it's the ratio of the haze size by the haze abundance. And then we are plotting the spectral irradiance, which we recorded using the generator. So what we observed was that we did see a pattern. So when we kept gases like CH2, nitrogen, and HCN, we took 4 gases, and we kept the relative abundance of one of them at higher, like say 50%, and all others were kept at a lower percentage. And then we checked the data, and like this we repeated for all the other gases to see the patterns. And we did see a pattern. For 3 of the gases, it was always in kind of increasing. But when HCN was kept at a higher percentage, we saw a different trend for the irradiance. So I'm just concluding this topic here. Like what we saw was a peak in the spectral irradiance as the haze abundance increases was seen, like for the different gases. And does the spectral irradiance with haze always have the same amount of point of change? So there was it's increasing. Then when something gets around 70% or 75% abundance, it decreases. So So what we saw was that the pattern was repeating for so many compounds, and does it always change around that abundance? So that was something which can be explored. And does this also happen when the haze particle changes, like sizes are changed? So there are so many things. So I've taken like around 90 plots, and then we analyzed some things, and then yeah. So also one more thing which we thought of exploring was to see the terminal velocity of the haze particle. So there are some more tools which help us calculate the terminal velocity of the haze particle and how do they fall through different atmospheric scenarios. So if you know, so it is important because if you simulate it and you know that okay, this is the size of the haze particle in a relative abundance like this, it has a terminal velocity of speed this. So when the telescopes will be observing data in future, so you know where to match it, you know where to classify it. So you like use alphabets to classify names, like sometimes club names like A, B, C. That is how also you see values. So if you have previously built up the classes, you can put them up in those things, and then that will help you determine the other properties and move on. And now I also be moving on to the another project which is continuing right now. So I won't be showing much results to it, but yeah. So I'm doing this with Dr. Jason Soderblom at NEID, and then this is actually on the main Titan. So it's not like Titan like exoplanetary atmospheres. It's on the Titan data observed by the Cassini. So Cassini, which became I think out of service in 2017. So my role here is to analyze the entire Cassini DIMS dataset to characterize spatial and temporal variations in the transmission of Titan's atmosphere around the two transmission windows, which I'll talk in more detail in the next slide. So this is like throughout the 12-year mission, like the Cassini spacecraft regularly observed Titan with the IXS and MEMS instruments. So there are a lot of data, but that's very low, that needs to be processed. And yeah, so there is a transmission spectrum, as you all know. It will help you know that what amount of absorbance has happened. You know, you all must have done the spectroscopy course last time or in your third sem, right? So yeah, so in astronomy, light from the host star passes through the planet's atmosphere, where it interacts with the atoms and molecules, and the ring around that, like the atmospheric ring of the planet, it will become opaque at some wavelengths, and then you will know like which chemical species strongly observed. So when you see that it's getting opaque, means there is more absorption happening. Like opaque as in the light you are receiving, that's turning more opaque, so more absorption is happening. So there is also some this. So this is the I think you all know, so I will not explain it over here. But like this was pretty interesting because when I was going through the data, it was like very. There were so many pixels over there. Like if you see the entire surface, it has some its own pros and cons. So transmission spectroscopy data is very sensitive to relative chemical abundances and the presence of cloud or haze particles within the atmosphere. And what I talked about is the 2 micron like transmission window. So they have some windows where you can observe the data clearly or like better because of I think WIMS had some of its flaws, like it put constraints on the Titan surface composition through the movement of reflected sunlight with some windows. Like there were some windows, so even in this range of 0.88 to 5.12 microns infrared range, there are around 8 windows, and one of them is 2 micrometer like a window which we want to explore. And in that, we have a lot of data, and we want to see how it varies. So you see, have an atmospheric data, you have all the data, latitude, longitude, distance angle, emission angle, different seasons. So you want to see how it is varying throughout. You know, you want to see is there any source of life? You know, is there some pattern which is similar to that of Earth? So that is how you relate this work and its importance. And I mean, this is like not like I'm also exploring this project. Like I came to a nice stage. So I should have some good results to show maybe next time I give some talk. But yeah, so the data was very low. So the data was an SQL database and processing took a lot of time. I had to download around 90 GB of file and it would fail if the Wi-Fi signal is down for even 1 second. I think it took me 10-15 sessions to download it. So good news is I'm finally able to refine the data. So sometimes you have to work with data which is not at all refined. And so I think taking some courses on like data analysis will definitely help irrespective of your majors. Because these days like a lot of theory has been already explored. So even if you know the theory, you need those skills. So currently I am analyzing the variations as I said. So yeah, this is about it. Yeah, enough for today. I hope it was not too boring. Do you have some questions, discussion? Yeah, sure. Not that successful of a method, but the light of the planet is bent by the gravity. Like so, there is gravitational interaction between the star and the planet, and then there is this you observe from Earth. So there is bending of light due to the gravitational interaction because of that. Yeah. So that bending of light due to the gravity helps you detecting the exoplanets.
And my second question was to probably get this a lot, but how much water did you find on Titan?
How much?
Water did you find on Titan?
Uh,
So on Titan, you work on Titan, right? The atmosphere of Titan.
oh, you are talking about Titan? No, I didn't hear. Yeah.
Yeah. So like, what kind of?
No, I'm not finding any water as of now. I'm not even like we are not included water. So it's mostly like methane and nitrogen-based atmosphere.
Okay.
So we are concentrating on that because nitrogen is also a potential harbor for life and hydrocarbons. So not the water thing right now.
So
Yeah.
I had a sort of like similar question about the detection bit. I can see how these techniques can be used to find out planets with stable orbits. What about the rogue ones?
So yeah, I also had a similar question like, what do you do about that? But then they are just develop a new technique. Yeah. But I was also surprised how can that exist? Like if it doesn't have, it's not revolving around the star. But that's a fact about nature. It doesn't orbit around the star. So maybe you observe that, you are observing and you randomly see some planet. I had an exactly similar question. So how do you even know that exists, right? Because it doesn't orbit a star. So you observe. So my guide told me that you observe it coming near Earth's surface maybe once and then maybe you again see it. So I don't know, that's really weird. But yeah, it exists.
And we talked about imaging, like using
Direct
that
imaging.
for the detection. Like
Yeah.
using that, we can like sometimes detect those planets which we are not able
Yeah.
to, which we do not think that will be present.
Yeah.
Like I think that may be one of the reasons. Like,
Yeah.
those which do not have a particular orbit.
Yeah, and that is why the number detected by direct imaging is also less, surprisingly. Although a lot of work is going on direct imaging method, but still the percentage is less as compared to transit and digital velocity.
And I had another question.
Yeah, I know. Tell me.
So can you pull up the transit like the data again? The two planets. We found one like one had like the stable tip and the other.
Oh, that's just an example.
Like, was this like incomplete?
This was not a complete transit.
Ah.
That was an incomplete. I just because so I put that in similar codes. Yeah. Okay. That is not a complete transit. There has to be a dip and then say this. The first one is still a complete transit.
Like in the last decade, planet 9 and planet 10 of our solar system have been hypothesized. But with the advent of James Webb Space Telescope in space, what are the future prospects? How would we find those strong evidence about them? Is there any credible evidence about planet 9 beyond the Earth?
Planet 9, like you mean in our solar system.
Yeah.
Yeah, I don't know much about it, so but it can help, because it has JWST is expected to go to lengths which we have not seen the previous missions go. So definitely, and it's giving even data is just coming like this. Like, you know, if you talk to some people working on it, that's like we are just just bound to it now. We went for it, and now the data is coming like anything. So maybe, or you can maybe check if someone is working on it. Because also we see the other plans like Pluto was excluded. So like, you mean the 9 and 10 are even beyond that, or like
Yeah.
yeah. So
In previous decade only,
yeah.
there was some hypothesis.
Yeah. Thanks for I didn't know about 9 and 10. Yeah. No, but definitely you can expect that.
Yeah.
Or maybe you can talk to someone from here. Yeah.
You display an equation for the transit depth,
Yeah.
right? Do you mean it's directly proportional to the
Ratio. Yeah.
It's directly proportional.
Yeah.
Okay, the square of the ratio.
Yeah. Square of that.
Okay.
If you want, I can send you a paper which has the on which my work was based. If you want Mandel and yeah, I will send you.
Okay. Also, another thing, so you said the transit curves, the shape is often different. So why would you expect different shapes?
Size is different.
But like the shape would be the same, right?
No, so one thing I also told, they just not provide us with the size information. They also are rich with another information which is includes the atmospheres, the absorption and all. So that is surprising. And it was also dependent on the host star. So maybe the two things are included here. The host star may be different for both of them. That can also happen.
But I was guessing the planet is passing in.
Yeah,
That would be similar.
but the data is like that, right? It's not like we actually devised it. So we get the data and the fitting leads to this. The same method of fitting leads to this. So that is the thing.
So one thing you can always add is that the height at which the planet is passing the star.
Yeah, that is
also
also.
watching upside down. So that will also affect the type of position.
Like it was passing above. Like there's a
Okay, some part of the
yeah.
planet.
Sort of an eclipsing parameter also had the extinction which will be caused by the planet's atmosphere. So that will also, because you are observing, you are not, this is an ideal case scenario which we call left hand side. There are many factors which add on what you are observing, what spectrum are you observing and what light you are observing. So it depends on that. Various extinction factors will change the light. Like what angle you are viewing, what will be the extinction factors, what will be the redshift analysis.
The extinction factor is due to the planet's atmosphere.
Yeah, planet's atmosphere and also how far the star points are, the planet also point mass and so basically they will change the light cost.
Also, even if everything is ideal, still you can get. So that's a atmosphere. Yeah.
So you were analyzing how, for example, moonlight will contaminate your data, right?
Yeah.
Or even sunlight distracted
Yeah.
from the atmosphere.
Yeah.
So because that was in the context of the Doppler shift, the wobble of the star. So I was asking the shift, like the Doppler shift would be similar, right? Even if you superimpose starlight or sunlight on it, the Doppler shift should still be observable. Right?
Yeah, but there will be contamination, right? It's more of instrumental than a theory.
Right.
So you are observing, and there will be noise. So you want to correct for that noise. So that is why this is taking a lot of time. I thought it would be simple to just correct for subtract the spectrum and all, but no. It has a lot of. I have not included everything. I cannot
and maybe you're
include.
missing something.
Yeah, I cannot include the entire work here like this then. Because that is what I also have to explain to people over here. Like that's it. Maybe you can see my thesis slides or the paper which I'm focusing on. So that is all the things are not included. Anyone else? Or you can ask any other thing also, like feel free.
I want to talk.
Yeah.
In this picture,
Yeah.
there are three planets passing at the same time. Is there any method to detect that?
Yeah, we have detected this like six planets orbiting a distant star.
But how are we gonna measure it if the dip is from like each planet? Like three or more, two or more planets are passing at the same time.
You will, as he mentioned, like you will see change
The
in
orbital
shapes.
period will be different. So
Orbital period, the change in the depth, shape of the depth. So when you don't have to observe just for once, you observe it over the years, and then you see what is the average and what are you constantly observing. So then that's how you classify it. And the orbital period, of course.
But we can't measure if there are multiple exoplanets using the radial velocity method.
Radial velocity method has its own flaws. So you can
Because
use
the
it
sun will
more for
wobble
ground.
around the, say, a combined center of mass of the system.
Yeah.
It won't matter if there is one exoplanet or multiple of them.
So, radial velocity is mainly focused on ground-based observations. Like you don't see space-based observations employing the radial velocity method. So it has its own flaws. I have had in one of the papers that I was doing. I mean, that's why we prefer some methods for some type of targets and some not for.
Like it's basically the signal processing thing. Talking about CCF, like cross correlation function. First thing I don't know much about it. Like could you explain more on this? Secondly, like whether this cross correlation function is same for like similar type of planets or like it's different for the same types of planets also.
It can be different. And the function which we have obtained here is used by some masking techniques. So it not only depends on the planets, but also on the technique you are using. What value of mask are you using? What method of masking are you using? Like so, it's all like you can change it. And more detail I will tell you in person because it's something which even I had to sit for hours with my guide and other faculties. So even they couldn't find good literature on it. So I think it would not be nice to explain over it. It will take some time. So I can explain it to you in person. And any other questions? You can ask anything in formal also. Come on, guys.
I see that you have to use many projects parallelly. So how do you like balance all that?
Okay, so I'm a human being. I